I guess we're not all here yet, but we're going to get started anyways, and we'll have the webinar recorded and on YouTube and available as a link on our soil health specialist page on the Cornell Soil Health website. So we're mostly here today to hear from Charlie White at Penn State on cover crop mixtures. But first, we're going to do some housekeeping with Aaron, and Aaron's going to discuss the process for getting the stipend and the stipend request forms for the soil health workshops you guys are all doing. So I guess, Aaron, if you want to start.
Okay, so I'm assuming everyone can see my screen. So good morning, everyone. So the long-awaited moment is here. I have the stipend request form, and then there's also a reimbursement form, but I'll go into that in a minute. Just remember, it sounds like everyone's phones are muted. I think there's a raise hand if you want to be unmuted. And there's a question in a toolbox. But it sounds pretty quiet on the other end, so I think we're good there. So I want to remind people that we do have targets for this grant. So we're trying to reach 400 farmers, 80,000 acres. But when you divide that out by 20 students, it's not too overwhelming. And then we dig a little deeper with a smaller subset of those 400 to try to get them to actually take that next step, not just show up and listen, but to conduct a soil health assessment or a soil health plan or do some sort of practice. And so the last webinar, I went over tracking that, and that tool is available online on the website. And then we also are reaching out to other folks that are participating in our field days as well, which I will be tracking that. So to the stipends, so as you were made aware before, there is a $300 stipend available. It is as a reimbursement. So you do the activity first and then get reimbursed. And it is really open, but you know, in general, it could be for presentations, workshop, field days, even on-farm technical assistance, again, taking soil health tests or something like that. So there is, you know, it really is open. We just try to give you some ideas here, and that's why I put it into this slide. And so here's a list of things, again, that could be used for speakers, transportation, porta-johns, that sort of thing, renting a backhoe or paying a farmer for digging a soil pit, something like that. It could be really open. You can be creative. So it's a two-part process. So prior to the event, you have to fill in this request form, which I'll show you in a minute. And then after the event, then there's a reimbursement form. So you need to have some information, basic information in both of these: the name, date, location of the activity. And we do have to spend the funds by January 31st, 2021. Hopefully all of you will have done your part long before then, but we do have a deadline as well. And like I said, all these forms are going to be available at that link there at the bottom. And I will send out an email after this with the forms, but also with the link in there. So I just wanted to show you really quick. So the one on the left side is the request form that you do prior to the event. So this is a fillable form. You could also just print it and handwrite in there and scan it, you know, whatever's easier for you, but it is a fillable form. And so you just need some very basic information. I'm not trying to make this difficult. It's not a competitive thing where we're giving some $300 and some not. Everyone is eligible for it. It's just we have to have a paper trail, you know, to how we're spending this money. So it's very basic information, but and then then you do your event, you spent your $300, and then there's again another fillable form, the one on the right that just has, again, where are we sending this check, who's it made out to, because some of you get it personally made to you, and some of it's for your company. So we just need to know those kind of details. And then, so these are the request forms, but you still need to keep track of everything in that other tracking tool that I shared last time. So I wanted to just give you guys a quick example. I did already have someone. This is Daniel, and I think it was Paul, who are going to have an event in July, and they sent in a request just yesterday. Their timing was perfect. So just earlier in the week when I was putting this together. So, you know, you can see it's really simple, just getting their information. Here's a brief description of the event, but, you know, they have some field trials and they're going to show these to some folks, and they're going to use this money to help pay for Faye Benson and his demonstration soil health demo trailer. So that's what that money is going to be used for. So he'll, so now I have their request. The only other thing to keep in mind is we are paying you, we have to do that W-9. So some of you have already done it to get reimbursed for things, but if you haven't, you will have to have a W-9 signed. So, so that's it. We're going to do this again one more time, a webinar, I mean. So we'll send out an invite, but we'll do it on Thursday, June 20th from 8 to 9. And we'll send out that Zoom information later. And I'm just putting this up for the record. So here's how to get in contact with us. And so I'll send all this out after this meeting. If you have any questions, you can contact me about it. So thank you. And then somehow I have to stop. Here we go. Stop sharing my screen. All right.
Charlie, can you elect to share your screen, or do I have to do that for you? You know?
No, I think I can do that. So I'll go ahead and get my presentation loaded up here.
So yeah, thanks, Aaron. Now it's my pleasure to introduce Professor Charlie White. He's a mentor, who was a mentor and committee member of mine when I did my master's at Penn State. Charlie is now an assistant professor and extension specialist of soil fertility and nutrient management at Penn State. Throughout his research career and extension career, he has conducted extensive research on how cover crops can be used to improve agricultural system sustainability. He completed his master's with the soil health guru Ray Weil in 2009, where he conducted research on the effects of cover crops on AMF colonization in corn and phosphorus availability. He's then the Northeast SARE coordinator for PA, and somehow managed to do a PhD at the same time with my master's advisor. So he was also part of the same big cover crop cocktails trial, which I was lucky enough to be a part of. And now in his current role as assistant professor, he does a lot of work on precision nitrogen management and understanding how to credit cover crop nitrogen supply to the following crop. So with that, I'll hand it over to Charlie.
All right. Well, thanks a lot, Joseph and Aaron, and thank you to all for participating in this project and in the webinar this morning. It's really exciting to see a cohort that's working together to advance your understanding of soil health and then share that with some of your clientele. So as Joseph said, I was part of a team and still am part of a big team at Penn State that's been studying the benefits and challenges of using cover crop mixtures, and trying to understand the different ecosystem services that those cover crops provide, and how best to manage cover crops to get those ecosystem services. So I'm going to share some work that we've done over the last 6 or 7 years to help unravel some of the mysteries and opportunities behind these cover crop mixtures. So probably a lot of you have been to field days in the fall, where a big tent like this is pitched in a cover crop field, and there's all kinds of hubbub about cover crop mixtures. Inside that tent, there might be a soil health guru like Ray Archuleta here, preaching the benefits of cover crop mixtures. Some of you have probably attended these events. Some of you are probably pitching the tent for these events. And there's a lot of interest in cover crop mixtures and the benefits that can be derived from mixtures. And a lot of this interest stems from a basic ecological theory that increasing biodiversity increases ecosystem functions. So this is kind of a classic graph about the relationship between the number of species you have in an ecosystem. In this case, it would be the number of cover crop species you have in a field and that ecosystem function. And as you go from 0 species, say a fallow, to 1 to 3 to 5, 6, or 7, or 8, the ecosystem functions increase. And those ecosystem functions could be something as simple as just having plant biomass there, but then we can drill down into other functions like weed suppression or refuge for beneficial insects, retaining nitrogen, supplying nitrogen to the next crop. The functions can go on and on and on that you try and get from cover crops. And the idea with the cover crop mixture is that by increasing the diversity, by having more species and more functional traits in the mixture, we increase the overall level of services that are provided. So that's kind of the basic theory that has led to so much interest and enthusiasm, is that potentially we can get more out of our cover crops by harnessing the benefits of diversity. So this project that Joseph mentioned and that I mentioned, we've had 2 rounds of funding from the USDA Organic Research and Extension Initiative to look at this. We've got a large team of interdisciplinary researchers. We've got farmer collaborators that have hosted a number of on-farm trials that I'll talk about today. So I want to credit that whole team in developing these results, and today I'm really just a messenger for that team. So our experiment at the research station, at least, was focused around 6 different species, and we grew these species in monoculture. And so we had 2 legumes, a red clover and an Austrian winter pea. We had 2 brassicas, canola and forage radish, and we had 2 grasses, cereal rye and oats. So these are 3 different plant families with different functions and functional traits. In addition to the 3 plant families, these 3 species happen to be crossed with a winter hardy growth habit. So red clover, canola, and cereal rye will reliably overwinter in the central Pennsylvania climate. And then Austrian winter pea, forage radish, and oats tend to winter kill in our climate. We planted these cover crops after wheat was harvested. So wheat was harvested in July. We planted the cover crops in approximately mid-August. And then those cover crops grow through the fall. Those that survive will go into the spring, and then they're terminated, plowed down. This is an organic system, so it's all tillage-based. And so they're plowed down, and then we planted corn. So that's the rotational window that we're looking at for this experiment. Now, in addition to the monocultures, we then assembled mixtures to target different functions. And so we have the 3 species nitrogen mixture. The goal with that mixture is to provide nitrogen for the following cash crop. And so we have a clover and a pea in there, but also we want to retain and scavenge nitrogen against leaching over the winter. So we have a winter hardy grass in there as well. We have a 3 species weed mixture, which is the clover, red clover, oats, and cereal rye. And the idea is to have the oats in there as an aggressive growing species in the fall to help suppress weeds, and then another aggressive species in the spring, rye, to help suppress weeds. But then since we are going into corn, we don't want to immobilize too much nitrogen, so we added the clover in there to fix some nitrogen. Next, we have the 4 species mix, which builds upon the 3 species nitrogen mix by adding canola. And canola adds some different tissue chemistry. So the brassica with some glucosinolates in the tissue when it decomposes. Also, the canola is flowering very early on, and so it could be attractive to beneficial insects. And then we added all 6 species together in our 6 species mix, which was kind of the highest diversity mix in this experiment, to see if we can maximize functionality through increasing species diversity. So in the experiment, the ecosystem services that we measured were biomass production. This is simply cover crop plant biomass in the fall and the spring And we take those measurements and we sum them together to get the sum of fall and spring biomass production. We looked at nitrogen retention. This bag here is full of what we call anion exchange resin beads. So these beads are positively charged, so as nitrate, and we bury this bag in the soil at about 1 foot deep. And as water percolates through the soil profile, it'll percolate through that bag, and that bag will trap nitrate. And then in the spring, we dig up that bag and measure how much nitrate percolated into the subsoil. We looked at nitrogen supply. We used a simple biogeochemical equation that takes the nitrogen in the cover crops and then adjusts it for the C to N ratio of that tissue to predict nitrogen supply. We measured cash crop production, which would be the corn. In this case, we're growing corn silage, so it'd be corn silage yields in the following crop. We looked at profitability, which was the change in silage yield or silage income if you were to sell that silage or have to purchase silage. The change in that income, which is really based on the change in yield from a fallow condition, minus the cost of the cover crop seed. So it's kind of a partial budget. We looked at pest suppression. So this here is a waxworm larva growing in the lab, and it's being infected by a fungus called metarhizium. And so this metarhizium is a natural beneficial soil organism that can control insect pests. We looked at weed suppression simply as the amount of weed biomass in the cover crop plots in the fall and in the spring. And then we looked at changes in soil carbon using the active carbon fraction. So this is the potassium permanganate oxidizable carbon there, POC, as some people call it. So to look at, so after measuring all of these indicators, we wanted to see how the cover crops influence these indicators relative to the fallow treatment. So we used a metric called a Z-score, and the Z-score simply looks at the difference in the indicator compared to a fallow treatment divided by the standard deviation. And so in all of our scores, a fallow treatment would have a Z-score of 0 because it's the standard. And if a species did better than the fallow, it would get a positive Z-score. So here, for example, would be a treatment that did better on nitrogen retention than the fallow. But if you did worse than the fallow, so for example, let's say this treatment did good at nitrogen retention, but actually immobilized some nitrogen, then you'd do worse than the fallow, you'd have a negative Z-score. And so for each treatment, we kind of plotted the Z-scores and then developed the average Z-score for each treatment. And that average Z-score was our indicator of multifunctionality. So let's look at the results here. So these are data from 3 different growing seasons combined together. On the x-axis, we have the number of cover crop species in the mixture. And then on the y-axis, we have the average multifunctionality. So this is the average Z-score here. And generally, there is a very poor correlation between the number of species and the average multifunctionality. You can see the regression line there is somewhat flat, and the R-squared value is very low. We have treatments like the Austrian winter pea that are a monoculture that did a very good job at multifunctionality, whereas the rye was very poor at multifunctionality. And then we even had mixes that were highly multifunctional, but mixes that were poorly multifunctional. So one of the interesting patterns here, though, is that our mixes the spread as we get to higher species, the spread is lower. So we actually get less variability as our diversity increases, but we don't necessarily get maximum multifunctionality through simply increasing species numbers. So species diversity is only one aspect. Species number is only one aspect of diversity. There's also what we call functional diversity, which looks at the different traits that the species have. And it's not necessarily so important how many species you have, but how many different traits or how those traits are distributed across the species. And so traits might be something like a C to N ratio, or a rate of biomass production in the fall, a rate of biomass production in the spring. And there's different metrics you can use to look at what functional diversity, how functional diversity is measured. But a metric that we saw that was important was this Rouse quadratic entropy. And I'm going to talk a little bit about what that means in a second here. But this was the best functional diversity indicator that corresponded the most with increasing functionality, multifunctionality. So again, on the y-axis here, we have our mean z-score, or our mean average multifunctionality. And that increased as our functional diversity increased as a metric of Rouse quadratic entropy. So, you know, these results pose several challenges for managing cover crop mixtures. The first challenge is even understanding what functional diversity is, right? It's very easy to understand species diversity as the number of species. You can put the number of species on a bag of cover crop seed, and everyone knows what that means. But I still have not seen a bag of cover crop seed with the Rouse quadratic entropy listed on the label. And even if it was listed, no one would know what that meant. So, you know, I think we need to start to learn about what functional diversity is, and that can help us manage cover crop mixtures. So I'm going to talk a little bit here about how functional diversity is measured, so that you all have some understanding of that and maybe can communicate this to some of your clientele. So functional diversity is all about the functional traits, and traits and the services that we get, the ecosystem services, are regulated by the traits of the species. And so some of the traits are things like I mentioned, like fall growth rate. Fall growth rate, the amount of biomass that's produced per growing degree day in the fall, that influences weed suppression. It influences nitrogen retention. It influences carbon inputs back into the soil as biomass. The spring growth rate influences nitrogen retention, carbon inputs. The C to N ratio is going to influence nitrogen supply. So thinking about the traits of these species, and then thinking about how an individual species, their different traits, how those traits fall out in what we call trait space. And so this is a three-dimensional graph that shows you axes of C to N ratio, the fall growth rate, and the spring growth rate. And each of the cover crop species in our experiment has certain traits of these three traits. They have certain values for these traits. So for example, oat has a relatively high C to N ratio. It has a high fall growth rate and a low spring growth rate. Red clover has a very low C to N ratio. It has a low fall growth rate and a moderate spring growth rate. So understanding how species fall out in this trait space. And these are just three traits that I'm showing you here, but you could have you know, dozens of different traits and have trait space in multiple dimensions, more than three, such that you can't even really visualize it. For example, you could have rate of root growth on this, or you could have flowering density, or, you know, propensity to host mycorrhizal fungi on the roots. You know, all of those are different traits. Here, we've just chosen to look at three traits because these are easy to measure agronomically, and they relate to some of the functions we're talking about, and people kind of understand what these traits are. So when you now have a mixture, what you need to think about is how does that mixture, how do the species in that mixture fall out into trait space? So for example, here's our three species nitrogen mixture. It's got pea, rye, and red clover in it. So if you were to connect those dots here and draw lines between them, it gives you kind of a volume of space that those species occupy. It also gives you how far apart from the centroid are those species. And if you look at biomass production, of those different species, you could look at how evenly distributed. So if all of the species had equal biomass production, all of these dots would be equal in size, and that would be a very even mixture. If, for example, rye had a huge amount of biomass and red clover had, almost no biomass, and pea had kind of a moderate level of biomass, that would be an uneven distribution of your traits in space. So when we look at the 3 species N versus the 3 species W versus the 4 species versus the 6 species, we can draw some comparisons. So for example, the 6 species mix occupies a larger volume in space. The 4 species mix has a slightly larger volume in space than the 3 species N or the 3 species W. But one of the things is that it's got canola here, and canola is kind of in the middle of the trait space. So there's actually an aspect of diversity called divergence, where you actually don't want species in the middle of your trait space because they're kind of only average players at each function. Really, a more divergent mix would have very few species in the middle, and you just have your kind of all-star players out on the edge here. So for example, the 3 species N and the 3 species W are highly divergent because all of their species are around the edges of the trait space. You've kind of got all-star players in each edge filling in kind of maximum functionality in those different edges of the trait space. So when we look at the metric that was most correlated to multifunctionality, it was the relative Rouse quadratic entropy. And what relative Rouse gets at is evenness and divergence. So you want a mix that does not have species in the middle. So for example, this 4 species mix here that has canola in the middle here, that would be less divergent, especially if you had a very large amount of canola biomass in the middle there. That would really affect your divergence. It would also affect your evenness. So the 6 species mix also has some species that tend kind of towards the middle. We've got pea and canola are kind of in the middle. Our 3 species mixes are very divergent, but the challenge would be to get even biomass production in those. To really maximize the Rouse quadratic entropy. So that's a little bit about how functional diversity is measured, and gives us some ideas about how to select species and how to manage those species. So the next challenge is managing for even biomass production. Let's say you planted a mix that was going to be relatively divergent, but you now need to have even species development over those species, or even biomass production. And in our experiment, what we saw is that over time, rye tended to dominate the biomass. So these charts show you the percent composition, which initially is based on the number of seeds per square meter, but then the amount of seeds that germinate, then the fall biomass, and eventually the spring biomass production. And you can see over time that in all of the species, the cereal rye, which is the green bar here, the cereal rye in the spring ended up being the dominant species. And so that's a big challenge for getting evenness, is that some species tend to dominate. We've seen at our research station, we saw that cereal rye tended to dominate. At some of the on-farm sites, we saw that canola tended to dominate. So on the right here is a picture of one of our on-farm sites where we planted a 4 species mixture and it just turned into all canola. So in the on-farm trials for this project, we planted the same seed mix, the 4 species mixture. We planted it on different farms. Those farms had different climates. They had different amounts of residual nitrogen in the soil, and we saw that there was completely different mixture expression in the fall. So the pie charts here down at the bottom, they show you the proportion of the mix that was each of the 4 species. And then the size of the pie chart corresponds to the overall biomass production. So for example, Center County, we had relatively little biomass production and it was mostly rye. If we look at Lancaster County, large biomass production, almost all canola. Montour County had the most biomass production, 3/4 canola, and about 1/4 pea, and very little of the other species there. So that's a challenge, because you can, create a blend and bag it up and try and distribute it to different farms, and it's going to behave differently. So we wanted to understand what are some of the factors that affected that behavior. So we took the same seed mix and we planted it at a research station at different planting dates, because we thought that climate, the amount of growing degree days in the fall, was going to influence expression. We also did different nitrogen rates. So we put out Chilean nitrate with or without Chilean nitrate crossed with different planting dates in the fall to see how that affected growth. And then we deployed that same seed mix at 6 or 7 different farms throughout Pennsylvania and even up into New York to see how it grew on the different farms. And when we looked at the data, we did some regression analyses to understand what factors influence the biomass production. So this is a 5-species mix now. We've added crimson clover into the mix, and we've switched rye to triticale. And each of these lines here indicates a relationship, a linear relationship. And the number there is the coefficient for that relationship. So for example, here, the number 44 means that for every milligram per kilogram or part per million of inorganic soil N at planting, so that's nitrate and ammonium combined, every part per million of that inorganic N will stimulate canola growth by 44 kilograms per hectare. Growing degree days between planting in the fall and December 31st, that would be our fall, kind of our fall growth window. Every growing degree day at a certain location or planting date corresponds or translates into 2.8 kilograms per hectare of canola growth. So you can see that canola is really stimulated by growing degree days as well as the inorganic soil N. And then canola actually has a negative effect on all of the other species. So these red arrows here indicate negative relationships. So increasing the canola growth tends to suppress those other species. And if you look at the relative magnitude of the impact of growing degree days in the fall on canola at 2.8 versus only 0.4 for triticale or 0.17 for pea or 0.34 for crimson clover, you can see a little bit of growing degree days is really going to push the canola, and a little bit of soil N is going to push the canola, and that's going to then translate into negative consequences for all our other species in the mix. So that's a challenge, and to me this kind of shows that canola is kind of like a keystone species, and I'd kind of like to see what would happen if we didn't have canola in the mix. Maybe, you know, the mixtures wouldn't be quite as susceptible to this suppressiveness and unevenness that the canola can create. But I'm sure there's other species out there that also act as kind of regulators of the rest of the cover crop growth. These are just some bar charts that show you from our research station experiment where we did 3 different planting dates of this mix with and without nitrogen, kind of what happens to the biomass. So here we have biomass of different species are the different colors in the bar chart. You can see it at every planting date when we add N compared to when we don't add N, the canola really, the biomass of the canola really shoots up by adding that nitrogen, and that increase in the canola tends to crowd out other species, and it reduces the evenness of our mixes. So it's not that farmers would ever go out and spread Chilean nitrate in the fall on their cover crop, but a lot of farmers do put out manure in the fall, and that can stimulate the sorry there, gotta turn off my phone. That can stimulate that manure in the fall can stimulate inorganic nitrogen and crowd out the other species. The other thing that can happen is high organic matter soils that get tilled in the fall can stimulate a lot of mineralization. And we saw that on some of our on-farm experiments where we tilled the soil to plant the cover crop. that stimulated mineralization and caused excessive growth of the cover crop. These are some pictures that just show the effect of adding that nitrogen. This is from the first planting date, and you can see how much more canola there is. It's almost all canola in the stand there where we added nitrogen versus where we didn't add nitrogen. You can see much more of the legume filling in and some of the triticale there. Okay, so the next challenge that we identified is that cover crop services are bundled and actually have trade-offs with each other. So originally I showed you this spider plot here with the different services, and when you plot them like this, it almost kind of makes you think that these services are independent of each other, and you could increase them all without having reductions in other services. But when we let those axes, when we tried to identify what axes were related to each other and maybe bundles, what we saw is that things like nitrogen supply, profitability, cash crop productivity, those are all bundled together. And that bundle is actually opposed to the nitrogen retention bundle. And so increasing nitrogen supply probably means that you're going to have a reduction in your nitrogen retention and maybe a reduction in your weed suppression. So there's these opposing trade-offs that need to be managed to improve overall multifunctionality. And depending on what your goals are, you might not be able to achieve everything at very high levels. And so you have to decide, are there some things that are most important to me on my farm that I really want to focus on those, or am I interested in kind of overall growth of the average, but not necessarily excelling at one specific function over another function? So on the nitrogen side, this is a particularly challenging trade-off because we often want to prevent nitrate leaching over the winter and also supply nitrogen to our next cash crop. And those were two of the functions that were mostly opposed to each other in our original data. And so understanding that behavior boils down to understanding some of the species characteristics, so legumes versus non-legumes and winter hardy versus winter killed species. And so grasses and brassicas only acquire nitrogen from the soil. They don't fix their own nitrogen, so they tend to be very good scavengers of residual soil nitrate. Legumes can acquire nitrogen through fixation through the nodules on their roots. So they're not quite as aggressive at scavenging nitrogen from the soil. They can also maintain high tissue nitrogen and low C to N ratios into the spring, which means they increase mineralization back to the crop. There's also the growth period. So winter hardy species like cereal rye and canola will continue to grow through the winter, continue to scavenge nitrogen and prevent leaching, whereas species like oats and radish winter kill, and then you're left with this period in the spring where there isn't continuing to be additional nitrogen uptake, and some of those residues might mineralize and possibly leach out nitrogen again into the spring. So when we looked at nitrate leaching data, that's what we have on the y-axis here, is data from our resin bags that I showed you earlier. So the amount of nitrate that leached into the subsoil under the different species. We saw different categories here. So we have no cover crop, the fallow treatment here, and a clover cover crop, which is a slow growing legume in the fall, had the highest amount of nitrate leaching, and that kind of makes sense. A moderate level here were winter killed species and pea, which is a fast growing legume. So here you can see what cover crop biomass looks like in the fall between the pea and the red clover. So that pea really does produce a lot of biomass in the fall, and that does place some demand on the soil residual nitrate level so that it draws it down a little bit, but it's still not the best. Pea tends to, in monoculture here, does tend to winter kill over the winter as well. But really our best performers at the nitrate leaching were mixes that included a winter hardy grass or a winter hardy brassica. And even just a 20% seeding rate of cereal rye in a mix was enough to get kind of a 90% reduction in our nitrate leaching. So a little bit of grass goes a long way in terms of preventing nitrate leaching. And so as we increased the non-legume seeding rate in the mixes, we got kind of slowly we pushed it all the way down, to almost no leaching under the rye monoculture. But really, we got 90% of the way there by only having 20% of the rye in the mix. Now, for nitrogen supply, this is a service that occurs after the cover crop is killed. And in a no-till system, you can let that residue decompose on the soil surface, or in an organic system like this, we're incorporating it into the soil with tillage. Then microbes will decompose that and mineralize the nitrogen. And the thing that really controls the nitrogen release here is the C to N ratio. And when we have a low C to N ratio, that means we have a high nitrogen concentration in the tissue. A high C to N ratio means there's a low nitrogen concentration in the tissue. And C to N ratios on the lower side tend to increase nitrogen mineralization because microbes release the excess N into the soil. On the higher end, there actually isn't enough nitrogen in the residues for the microbes to get all of their nitrogen demand that they need to grow their biomass from the cover crop residue. So then they get it from the soil. So they tie up nitrogen, call that immobilization. And then in the middle, there's kind of a range where there's just enough nitrogen in the cover crop residue to supply what the microbes need as they decompose that residue. There's not enough left over to mineralize, but there's not a shortage. So it's kind of a neutral level of immobilization or mineralization. There's neither a net increase or decrease in mineral nitrogen. So our cover crop species, where they fall on that spectrum, legumes tend to be very low. Radish tends to be on the lower side. Canola, it depends a lot on how long you let that grow in the spring. It can become very woody and have a relatively high C to N ratio. And then grasses, it depends a lot on how long you let them grow. The longer you let them grow, the more mature they get, the more lignified, the higher the C to N ratio becomes. Now mixtures, our research station mixtures, which tended to be dominated by rye, had a C to N ratio kind of 20 to 1 or higher. But some of our on-farm mixtures, which had more canola or had better representation of legumes in them, tended to be a little bit lower. And then when we looked at how corn yields were affected based on the C to N ratio, this dotted line here corresponds to the yield that we saw with our fallow treatment. And so as the C to N ratios got lower, so with a clover or a pea, we saw the corn yields went up. And then as our C to N ratios got higher, by adding more and more rye to the mix, our corn yields went down. So this is a kind of a direct reflection of the role of the C to N ratio in the cover crop residue at affecting nitrogen availability to the crop. So there's some trade-offs, and there's kind of a happy middle ground. So at the low end, we saw higher yields but moderate N leaching because these were either winter killed like the radish or legumes like the clover and the pea. On the other end, we saw low yields but good prevention of nitrate leaching because these were our grass species or winter hardy brassicas. And then in the middle, there's kind of a happy medium where we did a good job at preventing nitrogen leaching, and our yields were kind of moderate. They weren't too much lower than the fallow. And this is a case where you would have to come in and probably provide supplemental fertility because the cover crops really aren't providing nitrogen. They're not tying it up, but they're also not providing it. But you're protecting against nitrate leaching. So it's kind of this compromise there. So, to balance this trade-off, my suggestion is to use well-adapted legume with a low seeding rate of winter hardy grass or brassica. So, maybe 20% seeding rate of rye or triticale with 80% of a legume. I think that's going to give you the best compromise in terms of nitrogen performance. So in the end, what you do with cover crop mixtures, there's no simple recipe that's going to work for everyone. It really all depends on what do your clients want from the cover crop. There's lots of different functions that cover crops can provide. And I think for each individual context, you need to think, what are the most important functions? What do I need to get from my cover crop versus what could I potentially get from other resources on the farm? For example, from a fertility perspective, you can purchase external nitrogen inputs and manage that. You can't always purchase an offset in nitrate leaching, or you can't always purchase, an increase in beneficial beneficial insects or something like that. I mean, I guess you could buy some wasps or something like that, but I think bringing them in with a cover crop is maybe a bigger impact per se. So, to conclude here, diverse mixtures can increase multifunctionality, but it requires intensive management. It's not simply about picking a mixture with a high number of species. You have to think about the functional diversity and target functional evenness and functional divergence. And managing for that evenness can be a challenge. So you have to, think about species that aren't going to be excessive competitors. Think about your climate and your nitrogen status and maybe adjust the species you have in the mix or the seeding rates. And then think about how the services are bundled and how they have trade-offs, and whether there's certain functions that you really want to target, or is it okay to kind of hit the middle of that trade-off? Okay, so I'm going to stop talking here and hopefully leave a few minutes for questions and discussion. So thank you very much.
Yeah, thanks so much, Charlie. Even though I've seen you present a lot, you still manage to make it different and interesting in different ways each time. So I really appreciate it.
Yeah, my pleasure. So with my screen sharing here, I have not been able to see the chat window. So I'm going to stop my sharing here so I can read the chat, or I don't know if Joseph if you've been monitoring questions.
Yeah. I'll start. Morgan had one just now. Morgan works with NOFA and does a lot of work in pasture and grazing systems, and he wanted to ask, are there any plans to look at grazing these various cover crop mixes?
Yeah, I have not done a lot of extensive work with grazing myself. I have some colleagues here that have looked at that a lot. And so I guess I would, I haven't followed their results closely, so I can't speak to them, but I would just point out Jessica Williamson is our forage extension specialist, and Schuer Diker is our soil management specialist. Both of them have been looking at grazing systems with cover crop mixtures. Jess Williamson has been looking at interseeding cover crops into corn, and then in the fall they graze cattle on the corn stover and the cover crops. And so, I'd encourage you to reach out to her and find out about some of her results. Okay. Were there other questions from the group?
Morgan asked another one earlier, wondering if the canola is having any allelopathic effect, or if it's mostly just the shading from having extra nitrogen in the soil.
Yeah, my guess would be the shading. Yeah, my guess would be the shading, because I mean, it really does produce this broad leaf that kind of gets out on top of the canopy and really suppresses things. But, maybe there's some allelopathy component to it as well. We didn't look at that, so I can't say definitively that's not allelopathy, but certainly just looking at the results, there is a lot of shading that goes on.
Debbie wanted to know if you've done any work with cover crop planting date.
Yeah, so some of those results of the excessive growth of the canola in the fall are a reflection of the planting date. So we planted it starting in early August, mid-August, and then early September. And, the early August date gives you a lot more growing degree days in the fall. And so, so that stimulated growth of the canola. The other thing we've seen is that planting the cover crop earlier in the fall, actually in this case it's kind of summer because we're going after wheat harvest. The earlier we planted, the more weeds tended to grow. So that early growth or early tillage and soil disturbance stimulates a lot of weed growth, and then those weeds grow along with the cover crop. Seemed things worked a lot better if we plant, in terms of weed suppression, if we planted a little bit later, and just because of germination periodicity of the weeds, going in a month later to create a seed bed for the cover crops, we stimulated much fewer weeds growing. So planting date can also affect overwinter survivability. So for example, the peas, if you plant them too early, and I think this is also true for species like hairy vetch, if you plant them too early, they're more likely to winter kill. Whereas if you plant them on the later side, like in central Pennsylvania here, if we plant peas in kind of late September, it's kind of perfect. They germinate, they put out a few leaves, but they're nice and hardy through the winter, and then they put on a lot of spring growth. If the plant puts on too much fall growth, then it's at risk of dying over the winter.
And you guys stopped doing mixtures after corn because there wasn't enough time to really establish an even mix, right?
Yeah, that's exactly right. So the later you go, the fewer species you have to choose from. And it seems like even in central Pennsylvania, going in after corn silage, we didn't have the growing window to get any legumes or any brassicas established. So that's a challenge as well.
Brian asks, when a farm is planning to interseed cover crops and corn, do you have a suggestion of what corn herbicides are more likely to affect cover crop establishment?
Yeah, that's a great question. And I don't know off the top of my head, but that is something that you need to be aware of because some of the residual herbicides will affect cover crop establishment. This is something that Bill Curran, the former weed science extension specialist here at Penn State, has looked at quite a bit. And our new extension weed scientist, John Wallace, he's also looked at this. I believe in the Penn State Agronomy Guide, they have some tables now that show effect of different herbicide programs on interseeded cover crops. And so I'd refer you to that as a reference point. I know they've also written some newsletter articles in the Field Crop News and posted on our extension website. So that information is out there if you do some searching for it, but not being the weed science person, I haven't made room in my brain for that information.
Morgan also just had another interesting question. Are you looking at the same trials but with soybean as a follow-on cash crop rather than corn? What do you think that spider plot graph would look like?
Yeah, so we did, in this experiment, we did have soybeans in the rotation, and so we were planting cover crops after corn and then going into soybeans. And this is what Joseph alluded to of the cover crop mixes not really establishing. Really all we got was rye. So even though we planted mixes, we ended up with kind of a rye seeding rate gradient. So, our 3 species N mix, which was 20% rye and, 50% pea and 50% clover or something like that, the pea and the clover didn't establish. And so we ended up with just a 20% seeding rate of rye. So we were able to look at a seeding rate gradient there. It wasn't terribly interesting. Theoretically, you could go from wheat into soybean the next year and have an effect of the mixtures on the soybean. I think, weed suppression would probably be the same. Soybean obviously doesn't need the nitrogen supply. So, you're probably not going to get a hit in yield. There may be other factors that could affect soybean yields potentially, but we don't have the data for that. But certainly that would be an interesting thing for someone to look at in the future.
Morgan had another one: interseeding or post corn harvest establishment of covers? Question mark. What maybe benefits of drawbacks of each one or something? That's a big...
Yeah. So with the interseeding, I think that gives you the opportunity to establish some species earlier, and so you could get some legumes to take hold. I think it also, in the fall, we've had some really rainy falls where harvest of the cash crop has been delayed, and then the soil is too wet to get equipment in to plant a cover crop, and so kind of having that interseeded cover crop in there already is great, because then it's there. You don't have to worry if conditions are going to be right in the fall to get equipment in. Obviously you're going to do what you need to do to get your crop harvested, but if the soil is wet, you'd rather not come through with a second pass to plant a cover crop. So having that interseeded crop there, I think, is great for that. The challenge to the interseeding, challenges that I've seen are just getting good establishment. It depends a lot on the weather, and when you plant relative to canopy development and how the weather shakes out. So I think there's a risk for establishment failure, probably, but like I said, there's also risks for being able to establish your cover crop late in the fall. So I'm not sure that one scenario is actually riskier than the other. You've got to deal with interseeding. You've got to have the right equipment for that, and there's various ways to do that. But that's something that people have figured out. So so I think it's I think it's definitely a viable strategy that people should be thinking about and looking into trying that out.
Jody Putman had a question. She's a CC agent in Western New York. If growers' question is how can they build soil health the fastest, what are good cover crop selections in a typical corn soybean rotation that they can plant over winter?
In a corn soybean rotation, I would honestly, I would go with some kind of winter cereal, because it's going to be the most reliable to establish. So, something like rye, something like triticale. I think also thinking about letting that cover crop grow in the spring a little bit longer, I think could be a benefit, because you can really exponentially increase the amount of biomass that you produce, and then that's just additional organic matter that goes back into the soil. I've seen in Pennsylvania, I've seen a lot of farmers starting to do what they call planting green, which is where they let their cover crop grow relatively tall, and then before they kill it with an herbicide while the cover crop is still green, they actually come through with a planter and plant through it. And they're finding that with the green cover crop, it's easier to get the planter through than if it's already been killed and starting to die and desiccate and become woody. That's when they're seeing more of the hairpinning and whatnot. Also, keeping that cover crop alive through the spring. My feeling is that if you get a lot of spring rains, having that living cover crop there to transpire that water will dry the soil out a lot faster. Whereas if you kill it and leave that mulch on the soil, then when it does rain, you're actually trapping that moisture in the soil, and it takes that much longer to dry out. So, doing that planting green requires really good planter and requires some tinkering with your planter to make sure it's operating well. But I think that's a great strategy that I'm seeing more and more of our farmers in Pennsylvania turn to.
I had one thing I was curious if you've run into, and maybe this is more applicable if you're going to be applying some big source of fertility in the spring. Have you seen any work on oat and cereal rye bicultures of trying to seeing if that can maximize the fall fast growth of oat and the spring growth of cereal rye.
Yeah, I have seen that. So where I've seen that system are actually on dairies, and I haven't seen it with oat and rye. I've seen it with oat and triticale. But what they do is, and this is more in the southeastern part of Pennsylvania where we have a slightly warmer climate, but they'll come in after corn silage, maybe mid-September, and plant the oat triticale mix. And then in December, they'll actually be able to harvest that oat as a forage. And then there's a little bit of triticale still in the understory. And then in the spring, the triticale comes back, and then they harvest that triticale for a forage, and then they go back to plant corn silage. And this is a great system on farms that have ample reserves of manure that they need to dispose of and recycle that. So it can be a great source of forage, those additional crops. So, in those systems, they're actually triple cropping. So within a year, they get a triticale harvest, a corn silage harvest, and then a fall oatlage harvest.
Cool. Well, I guess I'm going to stop it just because we're at time, but I just want to thank Charlie White so much for spending time at 8 a.m. on Thursday morning with us. And thanks